Hello everyone, my name is Stanislav and today we are going to talk about artificial neural networks. Well, actually, each course dedicated to machine learning should cover some issues dedicated to artificial neural networks, and this course is not an exception. Within the framework of today's lecture, we will talk about artificial neural networks definition, existing structures of artificial neural networks, what is actually an activation function, what are the main types and their application areas. Moreover, I will provide you with some useful references which could be helpful to you to understand the mathematical background behind artificial neural networks. And finally, we will finish today's lecture with industry examples. Let's start our talk about actually what is an artificial neural network. Artificial neural networks are biologically inspired computer programs designed to simulate the way in which the human brain processes information. Actually, artificial neural networks gain their knowledge by detecting the patterns and relationships in data and learn through experience, not from programming. The possibility of training is actually one of the main advantages of artificial neural networks. And these methods are used typically for the following tasks like classification, pattern recognition, optimization, forecasting, decision making, control, automation, whatever, like many industry-oriented tasks. A concept of artificial neuron is very close to the concept of natural one. Like here in this picture, cell body, soma. The body of the neuron cell contains the nucleus and carries out biochemical transformation necessary to the life of neurons. Dendrites, it's like each neuron has fine hair-like tubular structures around it, and they branch out into a tree around the cell body. They accept incoming signals. Actually, the axon is a long, thin tubular structure that works like a transmission line. Synapses, like neurons, are connected to one another in a complex spatial structure. When axon reaches its final destination, it branches again, called terminal arborization. At the end of the axon are highly complex and specialized structures called synapses. The connection between two neurons takes place at these synapses. Dendrites receive inputs through the synapses of other neurons. The soma processes these incoming signals over time and converts that process value into an output, which is sent out to other neurons through the axon and the synapses. Actually, this is generally the basic algorithm how natural neurons work. Artificial neural networks are very close to this concept, and I would say that the concept of artificial neuron first time was founded about maybe 50, 60 years ago. So the concept is not really new. But anyway, up-to-date computational capacities give the opportunity to have deep artificial neural networks which are able to be trained and used in a form like we use our human brains. In the figure, for one observation, x0, 1, 2, and xn actually represent various inputs, like independent variables, which are fed into the network. Each of these inputs is multiplied by a connection weight, or synapse. The weights are represented as W0, W1, 2, 3, etc. Weight shows the strength of a particular node. In the simplest case, these products are added, summed, fed to a transfer function, which is called activation function, to generate the result. And the result is represented in a form of the output. A synapse is a connection between two neurons. Synapses have one parameter, weight. Thanks to him, the input information changes when it is transmitted from one neuron to another. Let's say there are three neurons that transmit information to the next one. Then we have 3 weights corresponding to each of these neurons. For the neuron with greater weight, that information will be dominant in the next neuron. For example, if we address the problem of color mixing. In fact, the set of weights of a neural network, or a matrix of weights, is a kind of brain of the entire system. It is thanks to these weights that the input information is processed and converted into a result. It is important to remember that during the initialization of the neural network, the weights are actually allocated randomly. Then we pass activation function, but about activation functions we'll talk a little bit later. In the right figure, a part of a neural network is depicted where the letters I denote the input neurons. The letter H denotes the hidden neuron, and the letter W denotes the weights. It can be seen from the formula that the input information is the sum of all input data multiplied by the corresponding weights. Then we give the input 1 and 0. So let W1 be equal to 0.4. Let me switch on the comments. Let it be like W1 equal to 0.4 and W2 equal to 0.7. The input data of the neuron H1 will be as follows. So it will be 1 multiplied by 0.4 plus 0 multiplied by 0.7. So the answer is 0.4. Yep. So now that we have the input, we can get the output by plugging the input into the activation function. Now that we have the output, we pass it on, and so on. So we repeat for all layers until we get to the output neuron. Having launched such a network for the first time, we will see that the answer is actually very far from correct, because the network is actually not trained. Well, now let's consider the concept of the activation function. Actually, activation function is important for artificial neural networks to learn and make sense of something really complicated. Their main purpose is to convert an input signal of a node in artificial neural network to an output signal. This output signal is used as an input in the next layer in the stack of the layers inside the artificial neural network. Actually, activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding the bias to it. The motivation actually is to introduce nonlinearity in the output of a neuron. If we do not apply activation function, then the output signal would be simply linear, 1-degree polynomial. And a linear function is easy to solve, yes, but they are very limited in their complexity, have less power, and have very limited application area for industrial tasks. Without activation function, our model cannot learn and model complicated data such as images, videos, audio, speech, etc. Well, now let's turn to the table and analyze each of the presented activation functions. So the first one is the binary step function, and it's some sort of a threshold-based activation function. If the input value is above or below a certain threshold, the neuron is activated and sends exactly the same signal to the next layer. So activation function, let it be A, is activated, yes, so if the input is greater than the threshold. The problem with this function is for creating a binary classifier, like 1 or 0. But if you want multiple such neurons are to be connected to bring in more classes, like class 1, 2, class 3, etc. In this case, all neurons will give you 1. So in some cases, we cannot decide. And for this reason, the application of such activation function is really limited for multi-class problems. Let's move forward and now consider signum function. And in mathematics, the sign function or signum function is an odd mathematical function that extracts the number of the real number. Linear function is almost never used except when you need to test a neural network or pass a value without transformations. Okay, well, now let's move forward and start our consideration with logistic activation function. Actually, it's one of the most common activation functions and its value ranges from 0 to 1. It shows most of the examples of the web, and it is also sometimes called the logistic function as well. Accordingly, if in your case there are negative values, for example, some variable can go not only up but also down, then you will need a function that captures negative values as well. It only makes sense to use the hyperbolic tangent when your values can be both negative and positive, since the range of the function is from -1 to 1. It's very important, actually, it is inappropriate to use this function only with positive values, as it will significantly degrade the results of your neural network. Now we move on to rectified linear units, ReLUs, and actually it is the most used activation function in convolutional neural network, which ranges from 0 to infinity. It gives an output x if x is positive and 0 otherwise. So it looks like having the same problem of linear function as it is linear in the positive axis. ReLU is nonlinear in nature, and a combination of ReLU is also nonlinear. In fact, it is a good approximator, and any function can be approximated with a combination of ReLU. Well, it is known and it was proved in the corresponding research literature that ReLU is 6 times improved over hyperbolic tangent function. It should only be applied to hidden layers of a neural network. So for the output layer, please use softmax problem, softmax function, and in case of classification and in case of regression, please use linear function. A soft plus activation function is a rectified base activation function that is based on the logarithmic mathematical function. Actually, it can typically be used in the activation of soft plus neurons. Well, now let's consider some structures. In machine learning, the perceptron is an algorithm for supervised learning of binary classifiers. Actually, it is a simplest ever existing artificial neural network. A binary classifier is a function which can decide whether or not an input represented by a vector of numbers which belongs to some specific class. It is a type of linear classifier that is a classification algorithm that makes its predictions based on a linear predictor function combining a set of weights with the feature vector. There is a way to amplify the power of neural network and increase the accuracy by the addition of the hidden layer. Yep. And actually, that sits, the hidden layer between the input and the output layers. And a multi-layer perceptron is a type of a feed-forward artificial neural network that generates a set of outputs from a set of inputs. A multi-layer perceptron is a neural network connecting multiple layers in a directed graph, which means that the signal pass through the nodes only goes one way. The multi-layer perceptron network consists of input, output, and hidden layers. Each hidden layer consists of numerous perceptrons, which are called hidden layers or hidden units. A feed-forward neural network is an artificial neural network wherein connections between the nodes do not form a cycle. As such, it is different from its descendant, like recurrent neural networks. The feed-forward neural networks was the first and simplest type of artificial neural networks devised. In this network, the information moves only in one direction, forward from the input nodes through the hidden nodes, if there are any, and to the output nodes. There are no cycles or loops in the network. Feed-forward networks have the following characteristics. So firstly, perceptrons are arranged in layers, with the first layer taking in inputs and the last layer producing outputs. The middle layers have no connection with the external world and hence are called hidden layers. Secondly, each perceptron is one layer is connected to every perceptron in the next layer. So hence information is constantly fed forward from one layer to the next. And actually this explains why these networks are called feed-forward networks. There is no connection among perceptrons in the same layer. Actually, again, it proves the title feed-forward network. In neural networks, a hidden layer is located between the input and output of the algorithm, so in which the function applies weights to the inputs and directs them through an activation function as the output. In short, the hidden layers perform nonlinear transformations of the inputs entered into the network. Hidden layers vary depending on the functions of the neural network, and similarly, the layers may vary on their associated weights as well. Well, now let me demonstrate to you a very simple example actually covering the issue of artificial neural networks overfitting. As you know, overfitting corresponds to the model which is too complex, thus this model covers noisy data and actually it demonstrates low generalizing capability of the artificial neural network. The data is shown in these diagrams in circles, and the circles are colored by the needed class. And the decision regions by a trained neural network are shown in red and green colors as well. In these diagrams, we can see that networks with more neurons can express more complicated functions. So, however, this is both very great since we can learn to classify more complex data, and it is bad at the same time since it is easier to overfit the training data. Like all machine learning models, overfitting occurs when a model with high complexity fits the noise in the data instead of the assumed underlying relationship. The plot shows that the model with actually 20 hidden neurons fits all the training data, but at the cost of segmenting the space into many disjoint red and green decision regions. The model with 3 hidden neurons only has the representational power to classify the data in broad strokes. So it models the data as 2 blobs and interprets the few red points inside the green cluster as outliers. In practice, this could lead to better generalization on the testing set. Well, based on this discussion, it seems that smaller neural networks can be preferred if the data is not complex enough to prevent overfitting of the model. However, it is not correct because there are many other ways to prevent overfitting in networks and like L2 regularization, dropout, input noise, etc. So in practice, it is always better to use these methods to control overfitting instead of just regulating the number of neurons in the neural network. This diagram illustrates simplified algorithms on how to construct artificial neural networks. So anyway, we start with loading data for training. Design artificial neural network and set the corresponding parameters. So we simulate the data and assess the convergence of the algorithm. So if it's converged, then we select the best design and test the best trained network with new data. So if we are able to get the highest quality metrics, so the algorithm terminates. If we aren't able to do it, actually we come back to the design of artificial neural network containing setting new parameters, initializing the network again, and simulation of the dataset. Well, previously in the lecture, we considered only feed-forward neural networks. Actually, in some sense, feed-forward neural networks are not able to learn. And now we are going to focus on backpropagation neural networks. And to start with, I would say that backpropagation algorithm was originally introduced in 1970s. But anyway, its importance was not fully appreciated at that time. So the main idea standing behind backpropagation algorithm is that you get the output of the neural network, measure the error based on the assessment of the network outputs with the ground truth, and then based on these error metrics, quality metrics on the algorithm, so you update the parameters of the artificial neural network to get the better result. In machine learning, backpropagation is a widely used algorithm for training feed-forward neural networks. Generalizations of backpropagation exist for other artificial neural networks and for functions generally. These classes of algorithms are all referred like in general form as backpropagation. In fitting a neural network, backpropagation computes the gradient of the loss function with respect to the weight of the network for a single input-output example, and does so efficiently, unlike a naive direct computation of the gradient with respect to each weight is calculated individually. This efficiency makes it feasible to use gradient methods for training multi-layer networks, updating weights to minimize loss, gradient descent or variance such as stochastic gradient descent are commonly used for these purposes. In this example, we used only one layer inside the neural network between the inputs and the outputs. In many cases, more layers are needed in order to reach more variations in the functionality of the neural network. For sure, we can always create one complicated function that represents the composition over the whole layers of the network. For instance, if layer 1 is doing 3 multiplied by x to generate a hidden output z, and layer 2 is doing z squared to generate the final output, so it means that the composed network will be doing 3 multiplied by x squared, so it will be 9x squared. However, in most cases, composing the functions is very hard. Plus, for every composition, one has to calculate the dedicated derivative of the composition, which is not at all scalable and very error-prone. In order to solve the problem, luckily for us, derivative is decomposable, thus can be backpropagated. So we have the starting points of errors, which is the total loss function, and we know how to derivate it. And if we know how to derivate it, each function from the composition, so we can propagate back the error from the end to the start. So this figure shows the process of backpropagation errors following this scheme, like input, forward calls, loss function, derivative, then backpropagation of errors. At each stage, we get the deltas on the weight of this stage. Like being more specific about the mathematics behind artificial neural networks, my suggestion to you would be to focus on a couple of videos. So please spend some time to watch this fascinating educational videos, giving the dynamic animated illustration of what is actually the mathematical apparatus and how actually the neural network works and how it is being trained. So it's just for your reference. Please feel free to use this reference. These videos are free open at YouTube. Speaking about different types of neural networks, I would say that there are so many neural networks out there that it's simply impossible to mention them all. Well, moreover, new structures, new configurations are created practically every month, maybe every week or every day. So if you want to learn more about this variety, please visit the Neural Network Zoo. The link is provided here in this slide. Actually there you can see all the existing neural networks represented graphically. So feed-forward neural networks is the simple neural network algorithm, so we have already considered it. For example, recurrent neural networks, which can process text, videos, or sets of images, become more precise every time because it remembers the results of the previous iteration. and can use that information to make better decisions. So recurrent neural networks are widely used in natural language processing and speech recognition. Well, now let's turn to the examples of artificial neural networks application in the industry. All these examples were taken from the published scientific papers, and the first paper is dedicated to artificial neural networks for short time forecasting of load and fuel consumption. So in this slide, you see the configuration of the neural network, generally the inputs which are needed to provide the output. And the upper table illustrates the initial data, which is also used as an input for the neural network to train and finally to test the algorithm. I would like to draw your attention to the results that the authors have managed to capture when using artificial neural networks, and they have provided the forecast of daily power flow through inter-system ties, which is presented in Figure 4, daily fuel consumption presented in Figure 3, and daily electrical energy consumption in the energy system presented in Figure 5. So the application of the neural network demonstrates high accuracy and feasibility of using these algorithms for this very specific problem under consideration. But now let me turn your attention to prediction of photovoltaic power plants output as far as it is the topic of your summer school project case. And there are many applications of artificial neural networks to PV forecasting and the internet. So please use Google search or use your university subscription to collect this information and investigate it. Maybe you'll find some interesting ideas and details there to solve your summer school project case. At this slide, we see the diagram of prediction using feed-forward backpropagation neural network. An input layer was used for data collection. A hidden layer was used for data processing by neurons, and the output layer for the results. Backpropagation is assumed as a very popular learning technique for feed-forward neural networks. Therefore, feed-forward backpropagation is defined as a model for forecasting parameters, and the diagram of prediction using feed-forward backpropagation actually is shown in this figure. Feed-forward neural network is defined as a type of multi-layer perceptron network with special input values. These values that are multiplied by their weight are led to the hidden layer by neurons. Okay, so let's move forward. Within the framework of predicting photovoltaic power plants output, the authors used meteorological and weather data, which is actually one of the very important ways and very effective ways to predict PV power plant output. Meteorological data such as temperature and solar irradiance were collected from the Malaysian Meteorological Department. That includes daily minimum, mean average, and maximum temperature, and solar irradiance starting from January 1st of 2006. So these data are converted according to the upper equation, and the authors calculate the daytime in order to get the better prediction accuracy. Yeah, so the equation used to convert the initial data is here. Yes, and the daylight time is calculated using this equation. The feed-forward backpropagation method is used as one of the algorithms within the framework of this study. Actually, the authors inside in this paper provided the research of other algorithms, but at the final stage, this algorithm was rejected and feed-forward backpropagation network was proved to be more effective. So the applied flowchart of feed-forward backpropagation is shown in this figure. Actually, as shown in figure, the prediction results are based on reading the testing and training data and using feed-forward backpropagation algorithm. So before the training process, all the data must be normalized. Various normalization methods are used for neural networks to increase the reliability of the trained network. Within the framework of this research, the min-max normalization is applied to the dataset. Well, a trial for investigation of the number of nodes in the hidden layer is evaluated to find the mean squared error of the feed-forward backpropagation neural network. Table 2 represents the training mean squared error and testing mean squared error, and actually a regression value for different numbers of hidden nodes for feed-forward backpropagation network. In addition, a graphical visualization of mean squared error and regression based on the number of nodes in the hidden layer is shown in the figure. The comparison between the simulated results of the feed-forward backpropagation and the real data for the power of the solar panel in 2010 is provided in Figure 5 and Figure 6. These figures illustrate these comparisons for January and February. Actually, the results for these 3 months demonstrate that the results are accurate for feed-forward backpropagation model. Actually, for this graph, I see 100% overlapping of the predicted values with the ground truth. The hidden neurons and the number of epochs in these calculations are 10 and 1000 respectively. Actually, the same comparison for 1 year, 2010, is provided in Figure 8 with 6 hidden neurons and 100 epochs. Well, although the number of hidden layers is increased from 6 hidden neurons to 10 hidden neurons in Figure 9, the level of accuracy is very close by considering Figures 8 and 9. And Figure 10 presents the regression of calculating data and the real data. Actually, as shown in the figure, the measured error is really low, and the selected quality matrix, which is R matrix, is calculated to be 0.999, so which is actually looks like very optimistic. Yes, but I do not pretend to tell the truth. Yes, but for me it looks like to be a little bit overfitted. Yes, because it seems that the neural network is very well fitted to describe the training set which was provided for the algorithm. Well, and in this slide, you may see the table with the predictions of the output power of the PV plant. The accuracy of the predictions was presented in the previous slide, so you may have noticed that the accuracy is really high. But one questionable point in this paper, and I want you to be aware of this within the framework of summer school case solution, is that you have the initial data set. Within the framework of the data set, you have certainly irradiation, photovoltaic power plant production, and many other features like times, angles, whatever. Of course, you can use irradiation as a feature to produce a forecast of the photovoltaic power plant. But let's think a little bit about practical implementation of such a system for power industry tasks. The question is, have you ever seen a weather forecast containing forecasting of solar irradiation for day-ahead perspective? Maybe there are some, but actually I have never seen a weather prediction containing solar irradiation. There is some data regarding the cloudiness, precipitation in the weather forecasts, but we never have the prediction of solar irradiation. For this reason, the next question is it really appropriate to use solar irradiation as a feature to forecast photovoltaic power plant output? The answer is yours, but from my point of view, it's not so appropriate because as far as we will not have this data in future when we are going to implement our system at the production site, it means that we will not be able to produce any forecasts. So please be aware of selecting features. And actually, I mean that you are really supposed not to just simply select the features based on the importance or just gaps, outliers, whatever. Yep. But I'm really encouraging you to think about the data set that we have provided from the point of view of simple persons, not a mathematician, not an IT specialist, not a power engineer. So just think about it and exclude those features which will not be helpful for you in creating the neural network model, because some of the features will never be available for you if you provide the forecast of the photovoltaic power plant for day-ahead perspective. Well, now we are smoothly coming to the lecture learning outcomes. And the first outcome consists of just a general statement that artificial neural networks can be applied to solve multiple regression tasks. But actually, I would add that artificial neural networks can be applied to other tasks, like classification, clusterization, etc. So this is a very powerful tool, but requiring big data sets in order to be able to train the artificial neural network. Actually, the structure of the artificial neural network depends on the problem under consideration. Activation functions may be adjusted using bias constant to use the problem under study. And it's very important. So you are free to adjust activation functions, and you are free to create the architecture of your artificial neural network to make it more efficient for the problem under study. So please carefully select the type of the neural network, and if it's needed, refer to Artificial Neural Networks Zoo, which actually describes the basic types of networks to be used for different purposes. And I'm really encouraging you to watch these previously provided 2 videos at YouTube, because it will provide you with a better understanding of the mathematical background on how artificial neural networks actually work. Not just artificial neural networks, but many other machine learning algorithms are really prone to overfitting, and overfitting may degrade generalization performance of the model. So it means that during the training process, you will have, let it be 99% accuracy, only 1% of error. But anyway, if we take another data set within the framework of the testing procedure, you will see that the accuracy of your model will be low, maybe 60, 70%. And what does it mean? That the model was really overfitted, and it was fitted to the existing training set. So it captures noise instead of real relations, real links, yes, between the features contained in the trainings. And artificial neural networks-based power industry tasks are mainly covered by forecasting, yes, but you may search the internet and find lots of other applications of artificial neural networks for real industry problems, including the problems of power industry, such as classification, clusterization, even control of robots, yep, whatever. Okay. Actually, it was the end of our today's lecture. Hope it was useful for you. And please investigate the references provided within the framework of this lecture. It was my great pleasure to talk about artificial neural networks today. And I hope to see you next time. It was Stanislav. Bye-bye.